Ho, ho, ho. So I thought today I would make a video tying all these different activities that we've done with oil leaking, stink bugs growing, amusement park entering and exiting. And so we're going to make a little video to tie all this together and actually introduce to you the concept of the definite interval. So maybe you're wondering why I'm dressed as Santa. Well, I mean, I always dress as Santa on Wednesdays. Apparently this needs a button here, I just noticed. Actually, no, I'll be going around Kettering this afternoon, or this morning, delivering hot chocolate to people. So come out and see us if you want. Get some free hot chocolate and some free food. I'll put in the, I'll post on Classroom where we'll be. So let's talk through this. So over the past few days, we've been looking at approximating areas under curves using rectangles, and we sort of ended up with three different scenarios that we sort of landed on. I'm going to just do 4 rectangles here. So we did where we used the left endpoint. Okay, so what do I mean by the left endpoint? What do I mean by that? Well, we're talking about, to get the heights of these rectangles, we use the left side of this, what we call the subinterval. Okay, we did a left endpoint, and we did a right endpoint. Okay, so that's a right endpoint. Now we're using the right endpoints to get the heights of those rectangles. And we did what we call a midpoint. So the midpoint was so you have some above, some below. Okay, and the midpoint is where you're using the middle of the subinterval to get the height of that rectangle. Okay, so essentially one of the things, I'll write that down, midpoint. Essentially, when we were doing this, whether we were talking about the amusement park, whether we were talking about stink bugs, these areas of these little rectangles, they represented something, okay? And it's important that we understand that. They represented an amount of something, because this function that we were finding area under was a rate function, okay? But all three of these things are what we call Riemann sums. Okay? All three of those are what we call Riemann sums. Okay? And what is a Riemann sum? Well, we're going to just make a general picture for a Riemann sum here. Okay? A Riemann sum is when you have an interval like A to B. Okay, so maybe in the stink bug problem it was 0 and 30. On the Kings Island problem it might have been 30 there too, I can't remember. The oil problem it was like 0 to 25. Okay, whatever A and B are. What a Riemann sum is you partition the interval. Okay, now partition is a fancy word for break into parts. Okay? We partition the interval into n subintervals. Subintervals. Okay? So in this case we were using 4. Okay? But there could be n of these subintervals. So here's 1, 2, 3, 4. Okay? And what a Riemann sum is, okay, hopefully you've seen this symbol before. This means sum, and this symbol actually means a finite sum. It means you're summing up a finite number of things, a countable number of things, if you will. What a Riemann sum is it's something that looks like this. It's when you're summing up, oh, my pants are falling down, okay? It's when you're summing up f of x sub I. Okay, x sub I could be any value in this subinterval that's going to give you the height of one of these rectangles. Okay, so maybe x sub 1 is right here, and that's going to give you the height. Then x sub 2 is right here. That's going to give you the height. And maybe x sub 3 is like right here. And that'll give you the height. And then maybe x sub 4 is right here. And that'll give you the height. Okay? But what a Riemann sum is when you're taking an f value and you're multiplying it by a delta x. Okay, now delta x in this case is that distance right there. It's the width of those boxes. It's the width of those rectangles. Okay? And you sum up each one of those. So this would be, I mean, if we were going to write this out, it would be f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x, and so forth. Okay? I realize that's running off the page, so I'm going to get out of the way so you can see it. But this is basically saying f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x. And you do that until you have all n of them. Okay, now in this particular problem, or not problem, but in this particular picture over here, this is a Riemann sum with 4 subintervals, 4 boxes, okay? 4 delta x's, if you will. And typically the delta x's are all the same width, okay? So we partition the a to b into n subintervals, and we'll just say, by the way, that delta x, if they're all going to be the same width, and if I have n of them, it's going to be this whole distance divided by n. So delta x is going to equal b minus a divided by n. Okay? But that's what a Riemann sum is. It's basically just summing up a finite, a countable, if you will, number of f of x times delta x. Okay? And there happen to be happening, these x sub i's here, these places that you're finding y values, are the way that you get the heights of those boxes. Now, over here, this is 3 special types of Riemann sums. A left endpoint, a right endpoint, and a midpoint. Those are really the only ones that we're going to care about a whole lot. So, I don't know that it's 100% necessary that I think it's important that we realize that you can use any value in here, and I think we already established that 2 days ago in class. Okay, but these are special Riemann sums where these values that you're effing, these x sub i's, are special places, either the left side, the right side, or the middle. Okay, and so the question is, and we've talked about this, we've sort of flirted with this idea. This is really bothering me. My collar is not connected. Santa would not be proud. So what we have been talking about is saying, okay, well, all of these, when we were finding these areas here that actually had some sort of meaning, when we were finding area under a rate function, whether it was a rate of change of stink bugs, whether it was a rate of change of people in an amusement park, or whether it was a rate of change of the quantity of oil in a lake. When we were finding those areas, it was an approximation of an amount of either stink bugs or an amount of oil or an amount of people. Okay, and it was an approximation. we sort of talked about and said, hey, how does that approximation, how can we make that approximation better? And everybody seemed to get on board with, well, just make the approximation better by making more rectangles. Okay? So if you think about this right here, what I have written right here, there are two ways that you could increase the number of rectangles. Think about the two different ways that you can increase the number of rectangles. And really, theoretically, if you do one of them, then the other one's going to automatically happen. Okay? One thing that you could do to increase the number of rectangles is to make n get bigger. And if n gets bigger, look over here, if n gets bigger, what happens to delta x? It gets smaller, because these are kind of inversely related, right? So if n gets bigger, delta x gets smaller. So now the question is there a way that we can make n get infinitely big and consequently make delta x get infinitely small? Okay? And the answer is, yeah, we can do that. Okay? We have a way to do that, and it's with limits. So I'm going to pause here to erase the board. Okay, so we're back. Got a clean board here. And so the question was, we had this statement here, f of x sub I times delta x from I equals 1 up to n. And you said delta x was b minus a over n, right? So what happens if we take the limit as delta x goes to 0 of this expression? Okay, now I know you don't know how to do that yet, and you may never actually know how to do that like symbolically or algebraically, but I think it's more important that you understand just conceptually what's happening here. What happens if we take this limit of this? What happens if delta x gets really small? Well, or, aka, the limit as n goes to infinity of I equals 1 to n of f of x of I times delta x. In both of these cases, what's going to happen? The number of rectangles, okay, is going to get huge, and they're going to get infinitely thin. Okay? What happens to that, what does this mean if that happens? Well, that's going to give us that exact area, actually. Okay? So the answer to this is going to equal that. Okay? Now again, we don't know how to compute this, but I'm just giving this a meaning right now. Okay? So notice what's happened here. First, the limit's gone, and now this sigma is now replaced by that integral symbol that you've seen before. Okay? But what's different? What's different? Think about what's different. Now, this integral symbol has numbers here. Okay? And delta x became dx. Okay? Now, if you think back to the derivative, dx, if we think back to what dx was, or in the derivative, we started off with calculating a slope, and we made that horizontal distance approach 0, and that became dy dx. Okay, that horizontal distance started off as a delta x. We may have called it h. We may have called it x minus c, but it was still a change in x. When you first learned slope back in Algebra 1, you learned slope as delta y over delta x, or change in y over change in x, right? So when delta x goes to 0, it becomes infinitely small. Okay? So this is actually going to give us the exact answer to that area. Okay? So we read this as the definite integral, okay, the definite integral of f of x, well, let's put from x equals how we read that. The definite integral of f of x from x equals a to x equals b. Okay? What is the definite integral? It's a sum. Okay? Yes, in this case, it ends up being an area under a curve, but we will learn down the road that the definite integral doesn't just have to mean area under a curve. What it is a sum. What is it in this case that we're summing? We're summing up every single y value between here and here, and we're multiplying it by an infinitely small change in x value. And we're adding that up, starting here and stopping there. Okay? And in this particular context, that's going to represent this area. Okay? But again, down the road, we'll learn that integration or integrals can mean other things. We'll add up other things, and it will result in a different context, a different geometric interpretation. I don't want you to leave this class thinking that the definite integral is the area under the curve. Okay. In fact, if you ask someone that in calculus, who's taking calculus, say, what's the definite integral, and they say the area under the curve, their view of calculus is very small. Okay. And so I don't want you to have a narrow-minded view of calculus. So, but right now, for our purposes, that's how we introduce the concept as an area under a curve, because it's a pretty easy concept to wrap our heads around, okay? So, at this point, we don't know how to compute this. Okay, in a minute, I'm going to show you how to compute it using a Desmos or a calculator, but we don't know necessarily how to compute it. Okay, what's more important is that we understand what it means. Okay, I would rather you understand what it means and have a good understanding of how what it means and its interpretations before you learn how to compute it. Because otherwise, you're going to get bogged down with computing it and lose the complete meaning of it. Okay. So what does this mean? I'm going to pause. So what does this mean? That's the question. You know, in a context, what does this mean? The definite interval, that didn't show up very good. The definite interval from a to b of some function. Okay? Well, in the context that we've already sort of investigated, we investigated 3 different rates where we were integrating those rates of change. And what we were getting, now we weren't doing it exactly, we were approximating, but what we were getting was an amount of something. We had integrated the rate of change of amount of oil, and we got an amount of oil. We integrated the rate of change of the number of stink bugs, and we got an amount of stink bugs, a quantity of stink bugs. We integrated the rate of change of people entering and leaving an amusement park, and we got a quantity of people. Okay? So, if so let's say if let's just say this, and if R of t is a rate of change of some quantity, then the definite integral from a to b of R of t is the change in the amount of the quantity from t equals a to t equals b. Okay? So if you integrate a rate of change between a and b, the answer, the number that you get, again, we don't necessarily know how to do this, we can approximate it, but the answer that you get is the change in the amount of that quantity from t equals a to t equals b. It's how many stink bugs were added or taken away from the house. It's how many people were added or taken away into Kings Island. It's how much oil was added or taken away from the lake. Okay? So if we were going to put those three contexts, if we were going to represent them symbolically, we would do it like this. So I think the stink bug formulas, which is the most recent one, I think the function that we did was 5 radical t cosine of t over 5. Okay? If we did this integral here, now again, we don't necessarily know how to compute it, we can approximate it, but if we computed this integral, it's going to equal the change in the number of stink bugs in the house from t equals 0 to t equals 30. It's going to be how many stink bugs were added or subtracted during that time interval. Okay? If we think back to the amusement park, let's just call it Kings Island because it's easier to write Kings Island. Okay, so if you go back to the Kings Island problem, okay, I think those functions were called E and L. I don't remember their algebraic definitions. I just remember their names. So if we just do this, oh wait, we didn't go that I-25, did we? It was like 24. Let's just do 24. Okay? If we do this, again, I don't remember what the formulas were for these functions, but if we did this, this equals the change in the number of people in Kings Island from x equals 0 to x equals 24. Now I got that was in hours, right? Okay? This answer, both of these answers don't tell you how many people are in Kings Island at 24. And this one doesn't tell you how many stink bugs were in the house at t equals 30. It just tells you how much they went up or went down. Okay? In fact, a couple of you, my pants are falling down again. A couple of you said, had messaged me, or I reached out to you by email because I looked at your stink bug problem, and your answers to the last two slides, your answer to the second to last slide, you had just the value of the approximations of the integrals. And the question was asking you how many total stink bugs are in the house, because you forgot to add on how many you started with. Okay? This is not taking into account any starting value. This is not taking into account any starting value. It's just the change, how much we went up or went down. And if we go back to the oil, back to the beginning of all this, I think the oil, I for some reason remember that function. I think it was 400 radical T. Okay? And I'm just putting 0 and 25 there. But in fact, I don't have to start at 0. Let's just start at 10. Okay? This integral here, because this number, or this function right here is a rate of change, this is going to equal the change in the amount of oil in the lake from t equals 10 to t equals 25. Okay, I think this was in minutes. Okay, how much oil was added or how much oil was removed? Okay, all three of these. Your you're integrating a rate of change, you're adding up a rate of change over some interval, it's going to give you the change in that quantity. Okay? So if I go back to the stink bug problem, the answer to the last question, or the second to last slide, I think is what it was, where you had the 3 different approximations, and it gave you a check mark if you gave you the right answer. If your answer was incorrect, it gave you an X. I don't know if you realize that. It took me some time learning how to program Desmos with some help from Mr. Gwyndon. I asked you to write 3 different approximations of the total number of stink bugs in the house on day 30. Okay? And so what that's going to look like is this. If we want the exact amount, it was going to equal 450 plus that. Okay? What's the 450? This is the starting amount. Okay? And then what's this equal? Okay? I don't know what it equals numerically, but conceptually I know that whatever the number is that this equals, it's the change in the number of stink bugs. Okay? Now I believe, well, I don't remember. I'm going to pause the video. In fact, I think I have to make a new video. I'm going to show you actually how you can, on Desmos, compute this integral. Okay? Just using a calculator to compute it. Again, we'll learn how to compute these things by hand, but you need to have a conceptual understanding of what's going on, and we're actually going to use this conceptual understanding of what's going on to teach you how to compute them by hand. So this whatever the answer to this is numerically is going to be the exact answer of the number of stink bugs in the house on day 30. Oh wait, let me add one more thing here. Change the number of stink bugs. This is important. From day 0 to day 30. Okay, we should always have something here when I'm representing what that change in quantity is. I should give over some sort of interval. Okay. So I'm going to pause this, or actually I'm going to stop this video. I'm going to make a quick video so I can show you on the computer how to use Desmos or your graphing calculator to compute a definite interval. Again, we're going to learn how to do these by hand. Don't you worry. You'll get sick of doing them by hand. Come out and see us this afternoon. I'm going to post that in Google Classroom where we are. Get some free hot chocolate. And that's all.